Can everybody see the pad, whiteboard?
Yes.
Okay. So can you see my drawing on whiteboard?
Yep.
Oh, nice. Okay. So before we started, so first I want to advertise our Pytorch tutorial on this Thursday. I mean, 2 days later. Our TM Junwang, he's an expert in all the popular um, deep learning libraries. So we specifically choose Pytorch as some introductory to give some tutorial on that because it's extremely popular. So in both academia and industry, someone may ask, why don't you introduce TensorFlow? We did that about 2 years ago, and then we found that, as the time went on, Pytorch becomes more and more popular. I mean, even more popular than TensorFlow, part because of Pytorch is so easy to use and user friendly, and TensorFlow is kind of weird. Uh, they are efficient, but it's very ugly to use and very inconvenient to use. Uh, but but I will post some tutorial given by our previous TM in our course website. So if you're also interested in TensorFlow, you can click that link and see some a good introduction. But on this Thursday, so I highly recommend everybody to join the lecture and then follow our TM. And if possible, you can try to install PyTorch and write down follow the TM to write down your first PyTorch training for some neural network. It's really worthwhile.
I have a quick question about that.
Uh-huh.
So for the homework, are we going to implement like this back propagation algorithm and stuff ourselves, or are we going to be using PyTorch?
In homework, you have to implement backpropagation by yourself.
Okay.
You're not allowed to use any third-party libraries.
Okay.
Because the key for for this class is to let everybody knows the fundamental things, the most important thing, the critical things. Although in the future, if you apply machine learning to solve your problems, it's not necessary to reinvent the wheels, right? To
Right.
do everything
Okay.
from scratch, right? But for this course, for this particular homework, you have to show that you really understand it.
I see. Okay, sounds good.
Okay. I think it's time for us to start. So first of all, I deeply apologize for the delay. Um, Last lecture, I did not realize the correct time when I plug in this iPad to show something. Um, I, I I was always watching the time, but the time was frozen. I don't know why. So today I just put my cell phone in front of me, and I'll look at the cell phone clock from time to time to ensure that we'll end at the right time. Okay. Um, a second thing. We're gonna release our final homework on this Thursday, and also there probably we're gonna release the deadline for our final project report. I plan to have the deadline as the 1 week after the final exam, so that everybody will have enough time to finish everything. I don't want to, because at the end of the semester, you have to prepare the final exams for quite a few classes and also project due, final homework due. So I want to be uh, as convenient as possible for everybody. Um, but we'll see, because we usually have some requirement, like after the final exam, what is the due for the final grade. So I need to double check that time um, that time interval. If I'm not wrong, it's usually about 2 weeks. So that means if you can submit the homework, if we can set a deadline like 1 week after the final exam, That should be fine. But I will double check. Okay. So let us finish up the backpropagation. So sorry again for the delay last week. We almost finished the whole introduction of backpropagation algorithm. However, because this is so critical, so I want to do this manual illustration of backpropagation again from scratch. So if you feel like you're very confident about every algorithm steps, please bear with me. I want everybody to be confident about this procedure, because you're gonna manually calculate some backpropagation procedure in your homework, and also you have to implement it in your algorithms and embed them in the stochastic learning framework. So it is really important to ensure everybody uh, is confident and feels comfortable about this whole procedure. Okay, so so again, let me first spend 1 minute to draw our 3-layer neural network as an example, right? So this is the input layer, x0, x1, x2, and I use 0 to index the input layer. And then layer 1, layer 2, and layer 3, like 1, 2, 3, and the output layer, right? So this is a feed-forward network. That means every node in the current layer will connect to every node in the next layer. So it will be like that. So remember, associated with each edge is a different weight, right? All the weights on the edges constitute the parameter set that determines this neural network, right? So our goal of neural network learning is to identify weights, right, on those edges. And finally, the second last layer, all the nodes connect to the output layer. Output node, which is denoted by Y, right? So I'm gonna use a dashed arrow, meaning that the output node, output neuron will feed to our loss function to calculate loss, right? So remember we introduced some like notation principle, right? So we use subscript to denote index of the neuron, right? So this is a Z0, and superscript denotes the layer index, right? So Z01, Z11, and Z21, right? So here will be Z02, right? Z12, and Z22, right? So what is a backpropagation, right? So it's very, you know, intuitive. So when we do the prediction, we're gonna compute from the input layer to the output layer, right? So this order is called forward order. Right? We call it forward pass because we're gonna sequentially compute the hidden neurons, their values layer by layer until we reach the output node, right? This is called forward pass. And the backpropagation is doing calculation in a reverse way, right? That is why it's called backpropagation. We start from the output layer and then go back, go to one layer um, before each step, right? Until we finish the computation of the gradients for every layer and reach the bottom layer, namely the input layer. So that's why it's called backpropagation. So the key idea of backpropagation is that we're gonna compute, and catch the partial derivative of the loss with respect to each neuron or node in each layer. Right? So in general, I can denote it by Z, H, like N, right? So I want to compute those guys, right, layer by layer in a backward direction, so that when I compute some new derivatives, I can reuse those results, and by just calculating a little bit more, so that I can save a lot of computation, right? I just read out the old values from the previous layer and calculate something new in the current layer locally, and then we can efficiently combine them together to get the partial derivatives with respect to the nodes in the next layer, and also the weights on edges connected to those nodes in the next layer. So we do this layer by layer until we reach the input layer. So that's the key idea. So if we do not do this, what's the consequence? If we do not use this idea, what's the consequence?
We have to recompute the partial derivative with each pass.
Yes, exactly, right? So remember last lecture, before we talk about the backpropagation idea, right? We calculate if we just naively apply the chain rule, right, to calculate any partial derivative with respect to some node, with respect to some weight on some edge, right? We're gonna look at all the paths from the destination node to the root node, right? And then just calculate the partial derivative along each path and multiply them together, adds up together, and then multiply the final partial derivative with respect to the destination node and weights, right? So this is backtracking. So even you go to the very bottom layer, and for the edges and for the nodes associated with edges, you have to go, you kind of backtrack to the output node. It's very, very inefficient. But if we use backpropagation, the benefit is that we'll never need to do the backtrack. Right? We only need to retrieve the results from the last layer. So if we compute some edge weights, the partial derivative with respect to some edge weights here, right? The only result we need is just partial derivative about those nodes, right? One layer above. That's the major benefit. Okay, so this is a summary of this key idea. So maybe 1 year ago, or maybe 3 months ago, maybe it's 1 year after or 3 months after, you will forget the whole details about backpropagation, but just have an impression about this key idea. So that after, so if you have to look at details, it'll be very easy to pick it up. It's not complex at all. It's very simple. This is very simple computation rules, but it's very powerful. So now let us perform some backpropagation with our hand, right? So as we mentioned, right, we start with the output layer and then going backward to the input layer, right? So we're gonna first look at the output layer, right? That means in the output layer, we're gonna compute partial derivative of the loss with respect to all the nodes in output layer, right? We only have one node in output layer, so only need to calculate partial L or partial Y, right? So obviously, this is determined by the loss function itself, right? If the loss function is a square loss, right? Y subtracted Y star takes square, right? So, and then you can just calculate fine. It's pretty straightforward. And now, suppose we have finished the computation of the output layer, right? So we're gonna use the result here to compute the partial derivative of the weights on all the edges directly connected to this output layer's nodes. Right? That means the weights on these three edges, right? So if we write them explicitly, it will be W.
Sorry to interrupt, but I think the screen sharing is frozen.
It's frozen again?
Yeah.
That's really bad. Okay. Let me reconnect. Sorry about this. How does that happen? Okay. How about now? Can
Just
see
it's loading the screen sharing.
It's loading. Okay. Does it show up?
Not yet.
Oh, it's very bad. Anything good happen? Still
No, we're
loading?
still stuck on that. Yeah.
That's weird. Zoom is quite unstable recently, right? I'm gonna stop sharing again. Let me plug out my iPad, plug in, and share again. How about now?
It just says you've started screen sharing.
Okay, let's just wait for a moment. Yeah, by the way, any question regarding our plan or schedule of the remaining classes, final exam, course project, and etc.? I mean, while we're waiting, I'm glad to answer any question.
We can see it now.
You can see it now?
Mm-hmm.
Oh, nice. Spencer asked, do we have 1 or 2 programming assignments left? We only have 1 homework left. Well, in that homework, you're gonna implement backpropagation and logistic regression. So I guess in regard to the homework assignment, there are only 1, right? But for the programming section, you're gonna implement 2 models. Any other question? Can you see my I'm joining on the pad?
Yeah, we can see that now.
Okay, hopefully it won't disconnect. Okay. Yeah, let us continue. So let me write down the weights on edges which directly connect to the nodes in the current layer, which is output layer, right? So it is W0, 1, 2. Remember our notation, right? So the superscript denotes the destination layer, which is, oh, sorry, it's not 2, it's 3, right? Target layer, the destination nodes layer, which is layer 3, right? 0 index is the source node, 1 index is the output node, right? So the edge in the middle, the weight is denoted by W 1, 1, 3, and W 2, 1, 3. Okay. So once we finished the computation of the partial derivatives with respect to nodes in the current layer, it's pretty easy to compute the partial derivative of the weights on edges directly connected to the nodes in the current layer. That means the output node, right? So we can see that. How can we see that? Let's just try to compute partial with this result, right? Compute the partial derivative of the loss with respect to the 3 weights, right? 1, 1, 3, L, 2, 1, 3, right? So we're going to use one example, right? Partial L over partial W, 0, 1, 3. How can I compute that? This guy.
Wouldn't it be partial L, partial Y, multiplied by partial Y, partial W0, 1, 3?
Yes, exactly, right? It's just a simple application of chain rule. That's it, right? So this one has already been cached, right? We do not need to recompute. The only new things is about this one, right? But we know that how we compute y according to z0, z12, and z22, right? They are linear combination. z12, w113 plus z22, w213 plus some bias parameter, right? So let me just put it as b2, right? So remember our rule that to compute the output node, we just compute the dot product. We do not need to compute the same mode activation function or whatever other activation function. So the computation of this partial y over partial each of those weight is pretty straightforward. And then you just multiply them together, you get partial L over partial W013, right? So similar procedure, similar computation procedure can be applied to this one and this one, right? So now we'll finish the computation for the alpha layer, right? So now we're gonna going backward, one step backward. So this is step one, right? Let me just denote it by step S1, right? So now in our step two, right, we're gonna.
All right, sorry if I interrupt. I just have one other question about just like in general in this. So we're trying to see how the loss function, we're trying to calculate the derivative of the loss function. But is that with respect to the input?
No, usually we do not calculate the loss with respect to the input because input is constant. We're not trying to update the input, right? We're trying to update the weights.
Okay, so we're looking for the partial L with respect to all of the weight inputs.
Yes.
Okay.
Yeah.
Okay.
But your question is good. I mean, in some models, like some unsupervised models, you might even do not know the input.
Right, that's true.
Yeah, and then in that case, if you want to jointly learn the input, well, you need to calculate partial L over partial x0, x1, x2. But the computation is just the same.
Sure. Okay.
Okay. So after finish the output layer, right? So we move one layer for backward. That means we move to layer 2, right? So our task will be to first compute the partial loss with respect to all the nodes in layer 2. That means partial z02, partial z12, and partial L, partial z22, right? So let us just use one example to show that because this is it's pretty straightforward, and I think everybody has an impression how to do that, right? So it's just a review, right? So to compute partial L over partial z12, right? The nodes in the middle, right? How can I compute that? Any suggestion?
Is it similar to the weights, just partial L, partial Y multiplied by partial Y, partial Z1?
Yes. Just apply the chain rule, right? Remember when we explain the graph, right? A graphical representation of the chain rule, right? It's the same graph. Right? So we know that Z12, it is only dependent on one node in the next layer, namely the output layer, right? Which is Y. Right? So we only need to apply partial L over partial Y times partial Y over partial Z12, right? So in the second last layer, namely layer 2, every node has only one parent node, right? So that's why there's no summation here. We only need to calculate partial L or partial Y, right? So, but later when we move to one layer backward again, right? Like Z11, you have 3 parents. So, and then you need to sum over partial L over each parent node, right? So, and this guy, partial L over partial Y, here has already been computed, right? So just read it out, right? The only thing we need to compute is partial y over partial z12, right? So we know how to we know how to compute that, right? According to the computation rule here, right? It's pretty straightforward. So, and this is something brand new, right? You have to compute it because you have never computed them before, right? You add them. So in this way, you compute partial L over partial Z12, right? Similarly, you compute partial L over partial Z02, partial L over partial Z22, right? So then we have finished computation of partial derivatives with respect to all the nodes in layer 2. Right? So next, based on this result, we can immediately compute the partial derivative of the weights on the edges connecting to the nodes in layer 2, right? So we can see that there are many, many weights, right? So I'm not gonna enumerate them all, right? So I can just write in general like partial W, because the destination layer will be layer 2, right? And it will be like IJ, right? You have many, right? Any weights on the weights on any edge that connect to one of the node in layer 2, they can be directly computed, right? So we can take a look at one example, like here, right? So here on this edge, so the weight will be denoted by the superscript is 2, right? In target layer, source node 0, right? In layer 1, and target node is also 0, right? So now, based upon the result here, right? How can we compute partial L or partial W 220? How? Any suggestion?
Would it be partial L partial Z02 times partial Z02 partial W002?
Yes, exactly, right? So it's pretty straightforward, because W002 is on edge connecting to the destination node, right? Remember, W002 is only dependent on the destination node. It doesn't depend on any other nodes above. I mean, I'm now saying on other nodes in parallel to its destination node. Right? Why? Because W002 depends on Z02, right? But it doesn't depend on Z12. Why? Because the weight here, it is the weight here on this edge depends on Z12. It's not W22, but 002. So when you compute it, just read out partial derivative of the loss with respect to its destination node, and then multiply the partial of the destination node over partial this weight. Right? And computation of Z02, it's just some nonlinear activation function about linear combination of the nodes in the previous layer, which is gonna include W002, right? So we have showcased how to compute in the last lecture. I'm not gonna repeat again, right? But the computation is relatively straightforward. So, to reinforce, right? Let us look at how we compute the partial derivative with respect to this guy, right? The weight on the edge connecting Z21 to Z22, which is denoted by Z222, right? So how do we, based upon the partial derivative results on layer 2, right, compute partial L over partial W222? Any thought?
Same way as above, but with Z2 instead of Z0.
Yes, exactly. Just remember that, memorize that rule. Yeah. Just look at partial derivative of L over partial derivative of the destination node, which is Z22, right? and times partial Z22 over partial W222, right? This is something new you have to compute, right? But this guy has already been computed and cached, right? You just read it out. So you can just follow the same way to compute all the weights, compute the partial derivatives for all the weights on the edges connecting to Z02, Z12, and Z22. Right? So now we'll finish the computation of layer 2, right? So in the next step, we're gonna move one layer backward, meaning that we have arrived at layer 1, right? So again, we first compute the partial derivative of the loss with respect to all the nodes in layer 1, which includes Z01, Z11, and Z21, right? So now, let us use the middle node in layer 1 as example, right? So how can we compute partial L or partial Z11? Any thought?
So the chain rule again, but with each node in the previous layer summed up.
Why?
Since Z1 depends on each node above it.
Yes, exactly, right? So here, just be careful, because Z11, right, when we look at how it connects to the next layer, meaning layer 2, right, it actually connects all the nodes in the next layer, Z02, Z12, and Z22. That means it depends on both, depends on all nodes in layer 2, right? So let me draw it explicitly. Which color should I use? Maybe use this one.
Or I guess rather, wouldn't it be that like Z02 is dependent on Z11?
No, it's not dependent on Z11.
But isn't Z02 isn't a function of Z01 or Z11?
No. You should view like, so when we move to layer 1, so we have a collapsed view of the loss function, which is a function of all the nodes in layer 2, right? So it will be the function of Z02, Z12, and Z22, right?
Okay.
So we're gonna compute this function, its partial derivative with respect to all the nodes in layer 1. Right? So just look at, okay, which nodes depends on or connects to the current node I'm gonna take derivative. Like if you look at Z11, right? We know that, okay, Z11 connects to Z02, Z12, and Z22. So they're dependent on all the 3 input variables.
Right, but like I guess like what I mean is the value of Z11 does not depend on the value of Z22. Because that's down the
Z11 does
that's
not.
down the net.
What?
Sorry, just keep going. I think it'll clear things up for me.
Yeah. I mean, Z11 is definitely dependent on Z22. Remember, Z11 connects to Z22, right? If you compute Z22, is actually a nonlinear activation function of the combination of
right.
Z.
So Z22 is a function of Z11.
Yes.
Yeah. Okay.
And similarly, Z12 is also a function of Z11. Z02 is also a function of Z11, right?
Yeah.
Yeah. If you confused or feel uncomfortable, just to remember the graph illustrates everything. If there is a connection,
right,
that shows the dependency for sure. Okay, so know that because Z11 connects to all the nodes in layer 2, right? In one layer above, right? So we know that the computation of each node in layer 2 will involve Z11. That means if we apply the chain rule here, we're gonna use summation, right? We need to compute partial L over partial Z02 times partial Z02 over partial Z11 plus partial L over partial Z12 times partial Z12 over partial Z11, and then plus partial L over partial Z22 times partial Z22 over partial Z11, right? These three guys have already been computed in the previous step, right? In S2, right? So we can just read them out, right? What we need to do is just to compute this three, right? These three you have to compute from scratch because you have never computed them before, right? And the computation, again, is dependent on the activation function, on also all the weights that combine Z01, Z11, Z21, right? Feed them to the nodes and then perform nonlinear activation function. So similarly, we can compute partial L or partial, say, Z01, right? So this guy. Okay. So you can see that in layer 1, actually every node connects to all the nodes in the layer above, right? That means if you compute partial L over partial Z01, you have to do the summation again, right? Apply the chain rule. Partial L over partial Z02, which is here, right? And then partial Z02 over partial Z01, right? Plus partial L over partial Z12 times partial Z12 over partial Z01 plus partial L over partial Z22, right? This guy, right? Remember, this guy also connects to, are connected with Z01, right? So it's partial Z22 over partial Z01, right? So just apply the similar computation procedure, right, for all the nodes here. So suppose now we have finished computation of the partial derivatives with respect to all the nodes in layer 1, right? So here, right? So then the remaining thing is to use them to calculate the partial derivative with respect to weights on the edges connect to the nodes in layer 1, right? That will be the nodes stay on those edges, right? So you can see many nodes. So again, to reinforce the idea, I mean, it's extremely simple, but I just want to reinforce this idea, right? So I'm gonna ask a silly question again, right? So suppose I want to compute the partial derivative with respect to this particular weight, right? So which is denoted by W superscript will be 1 and 0, 0, right? So how can we compute partial L or partial W001? Anything?
We should be able to take the partial of L with respect to Z01 times the partial of Z01 with respect to W010.
Yes, exactly right. This is just a rule. It's easy to memorize even, right? So similarly, if you want to compute partial derivative with respect to this weights, right, which is W101, right? So again, you're gonna look at the destination node, right, and then read out the partial derivative with respect to the destination node, then times partial destination node with respect to the target weight, right? Oh, sorry, this is 101, right? So just apply it again to compute the partial derivatives of all the edge weights which connect to Z01, Z11, and Z21. Right? And now we'll finish the computation for layer 1, right? So what's the next step?
I guess we'll move on to layer 0 then.
Yeah, and because if we are doing training, right, supervised learning, we know that input are there at constant, right? So we do not need to compute the partial derivative about the inputs. Then we just stop here. Right? We finish the backpropagation. Right? But if you want, like the computation of partial L over partial x0, x1, and x2 have nothing different with the computation for z01, z11, z21. So it's done. Right? Any questions so far?
Yeah, could you remind me what we're going to be using these derivatives for again in our algorithm, or like where are we going with this?
Okay. Yeah, that's a very good question. So once we use backpropagation to compute the partial derivatives over every edge weight, right, we can use this gradient or derivatives to update those edge weights, say in the stochastic gradient descent framework. That connects to our general learning framework. Remember, when we talk about how to train a neural network, we talk about, okay, we can just apply stochastic gradient descent, right? So every time we just look at one sample and fake the sample and multiply them, the original size of the training data, or to fake, to duplicate, to fake a data set and calculate some stochastic objective, right? And then that is our L, right? And then we just calculate the partial derivative of this stochastic objective with respect to all the edge weights, right? We got the stochastic gradient. Then we just update the weights.
Yeah, I can see how like that kind of mirrors what we've done before with stochastic gradient descent. I guess it's hard for me to figure out exactly how we're doing that update with those derivatives. I guess is my next question.
Yeah. So yeah, let's proceed. Let's proceed. We will look at this. We'll look back to the stochastic gradient descent framework again, right? And then you can imagine that you're essentially plugging backpropagation here. But before we review this SGD again, right? Any other question regarding, the details of backpropagation? So everyone is comfortable, right? Okay, great. So yeah, going back to a question, right? So we need to, connect to the whole training framework we discussed before, right? How do we train a neural network given the set of training data, right? So let us first look at this, right? So we mentioned that we can use the stochastic gradient descent to train our neural network, right? So we can define a loss function, right? The loss function typically use loss function will be L2 loss, right? So for every training example, given the current weights of the neural network, right, we can make forward pass to make prediction, right? And this is essentially our output layer, right? Our output node, right? And then we calculate loss against the ground truth label, right? We got loss, and then we sum over the loss of all the training examples, we get our total loss, right? So our goal is to minimize the loss on the training data set to find the optimal neural network weights. Those guys staying on the edges of our neural network, right? But how can we do that, right? Obviously, ideally you can compute the true gradient of this total training loss, right? But that will be very inefficient because modern neural networks are usually contains millions or even billions of parameters, hundreds of layers, and you have to feed them. They are data hungry. Meaning it is often times you have to feed them like millions of training examples, billions of training examples, even trillions of training examples, right? So if you compute the exact gradient That means you have to go through every training example to get the true gradient. Right? That's very, very expensive. So how to do that? A very cheap but effective way is to use stochastic gradient descent, right? So this is the algorithm steps. We're gonna first randomly initialize the neural network weights, right? And then we go through the whole data set multiple epochs, right? Each epoch we're gonna go through the data set once, right? Inside each epoch, we'll first randomly shuffle the training set, and then we'll look at the training example one by one, right, in this random order. And for each training example xi, yi, we can treat this example as the entire data set, as we mentioned before, right? We can calculate the loss for this particular training example, right? And multiply it by the size of whole training data to fake the training data, right? And plus some regularizer, we got some stochastic loss L, right? And then you just calculate gradient of that stochastic loss, which is called a stochastic gradient, right? But how can we calculate stochastic gradient?
Back propagation.
Yeah, the back propagation. The exact procedure we just mentioned before, right? Because the loss itself is very easy to compute because it is only on one particular training example, right? But the remaining thing is how, given this loss, how can we calculate the derivative with respect to every weight on your network, right? Then that involves some back propagation procedure, right? You're gonna starting from the original stochastic loss and then calculate the partial derivative of that loss with respect to every node, every weight, layer by layer until you reach the very bottom input layer. And then once you get this stochastic gradient, of course, you need to multiply some step size and then update the neural network weights accordingly, right? And of course, if you want to ensure convergence almost surely, you have to schedule your learning rate to satisfy some criteria, right? You mentioned that before. The summation of those step sizes should diverge, but their square summation must converge, right? And then after you pass through all the training examples, you finish one epoch, and then you go through the data set again, right, to do the next epoch, right? So until you finish all the big T epochs, you return the current set of weights on neural network as your learn parameters. Does it make sense? Any question? Okay, so now I want to go back to one slide before, right? So the techniques we mentioned with the back propagation is actually the key techniques. So in the future, I mean, if you have a chance or you would like to dive into deep learning a little bit more, you will see not only this feed-forward architectures, you will see many architectures, but nearly all kinds of neural networks are kind of layer by layer hierarchical structure, like convolution neural networks, and they just redefine how nodes in different layers are connecting to each other. But the whole philosophy has never been changed. It's always like, okay, I'm gonna back propagate the derivatives from the output layer and going step backward each step each time, and until we reach the input layer. And someone in early development, like 3 decades ago, like neural network researchers, they always handwritten, manually written the backpropagation code by themselves, right? But nowadays, we do not suffer from that. So nowadays, people have developed a variety of powerful and general computing platforms. And in modern deep learning platforms and libraries, you never need to implement backpropagation by yourself. Actually, in many libraries, you never need to care about how to compute the gradient. What you need to do is just define how do you compute loss. And then they're gonna automatically compute the partial derivatives with respect to all the weights by for you. And it's very mature, numerical stable, and it's highly efficient, and it's parallelizable to GPUs or clusters. So actually, nowadays, I mean, neural network researchers really happy, much happier than before, because we really need to consider the training details. All those are done automatically by libraries like Pytorch, like Theano, like TensorFlow, like JAX, like MXNet, a lot of like frameworks. So, so from this class, we do want you to know the details, right? The fundamental principles of this and the key ideas of this. But in practice, and in the future, if you want to develop neural network models and algorithm, you should focus on the model design, your idea, right, and your prior knowledge how to incorporate the training procedure. You'll never need to worry about, the low-level implementation details. Yeah. Okay, I think we have finished the backpropagation chapter. So before we look at another topic, any questions so far?
Do we store the weight vector as like a single array, or do we do it like an array per layer and then like split the gradient up into that? How do we store the weights?
Oh, that's a great question. So in your own implementation, it's up to you, because the problem scale itself, or model scale itself, is small. So you can start by just a simple array, or you can by a vector, or you can even place them in a big array. It is up to you. Whatever convenient you feel comfortable is okay. But in modern implementation of the neural network platforms, they use general form. It's called tensor. So you can roughly think of tensors as cubics or high-dimensional cubics. So they're going to assume, okay, every input x, y, output y, or the weights are represented by all kinds of cubics. So they have a way to implement this backpropagation procedure and represented them in terms of tensors or cubics, and also how to connect them together. Is actually there is a concept called operational graph or computational graph. They're gonna create those computational graph when you write down your own loss function, because when you write down loss function, that is how do you perform the forward pass procedure. You actually specify the dependencies between the nodes, weights, inputs, all kind of stuff. So once you write down, when they ask you that kind of code, the kind of like simultaneously generate computational graph that allows you to follow that graph to back propagate those derivatives and the chain rule, all kinds of stuff. That's the general idea.
Okay, thank you.
Any other question? Okay, nice. So now I'm gonna quit from the whiteboard, and we'll look at the slides again. I think it should be this one. Can you see the slides? Neural networks and practical concerns. Okay, so is the transition okay? Nice. Okay, so the last topic. Sorry. about neural networks are about some suggestion in practical applications, right? So so far we haven't discussed, we haven't introduced the definition of neural networks. How do we conduct prediction with a given neural network, which we call it a forward pass, and how do we perform the training, right? So of course, the general framework is the same as other models. It's just the stochastic gradient descent, right? The major obstacle is how to efficiently compute the gradient with respect to every weight, right? So that's why we introduced the backpropagation, right? And once you know how to compute backpropagation, then all the other things are the same as you did before, right? And then the final things is about how do you apply neural networks in practice, right? Or a few warnings when you apply neural networks in practice, right? So one interesting experience I want to share with you guys is that um, the tuning of neural networks is kind of magic. So in other words, there are not like systematic way or theoretical guarantees about how do you tune a perfect running neural networks. So that means if you're a good engineer, your neural network might be far better than some fresh guys or inexperienced person. So that's some kind of like some criticism to the neural network world as well, right? You see some people claim that okay, when I construct neural network, when I when I set the architecture in that way, choose the activation function, choose the initialization, how to tune the learning and all kinds of stuff, I can make my network works really better, works really good, right? But someone just cannot let the network uh, work well, and might be even worse than logistic regression or decision trees. That is possible. So I mean, in other words, neural networks are very powerful, but to make it powerful, you have to spend a lot of time and efforts on that, and which are not explained by some theory. Okay, so there are in general three types of practical concerns when we apply neural networks. First, how to address the problems with stochastic gradient descent, and second, how to prevent overfitting. Is actually this is a very common problem for neural network, especially if you intentionally make your network larger, deeper, wider. It is very easy to overfit the trained data and then cause bad generalization accuracy on the test data. And how to choose number of hidden layers, right? That is about how to identify the architecture of the neural network. Right? So first, training neural networks with SGD is not easy stuff. Why? Because SGD, stochastic gradient descent, is actually not working with a true gradient. You're always working with some approximate gradient, right? So the typical behaviors of SGD is kind of an oscillation. If you look at the error on the test data, or if you look at the objective function, right? So someone asked about homework 4, right? And asking why do you ask ask me to show the function curve when I use the stochastic subgradient descent to train the SVM? I just want to give you an intuition, like how the training behavior or learning behavior of stochastic subgradient descent or stochastic gradient descent, and to give you a sense on that. It's not any other reason. It's not some reason to torture you. It's just to give you a sense. How do you tune that and how the learning curve will look like? Okay. So, because neural network is even more complex than support vector machines, right? Support vector machines is just a quadratic convex function, right? It has nice property, right? There's only one global minimum. But for neural network, for neural network, it's typically non-convex, right? That means you have you might have many local minimum, local maximum, whatever, right? So it depends if you run run SGD, right, starting from different initialization, you end up with different local minimum. It's very possible. So initialization matters a lot, much more than training support back machines. And also, the SGD is hard to diagnose, hard for us to diagnose convergence. Why? Any thought? In other words, if you use SGD to train a neural network, how do you conclude that you have converged to some local minimum here or here? How do you conclude that?
Possibly using the gradient, right, and seeing, all right, well, our gradient changed a lot.
Yeah, that's a good suggestion, right? But the problem is that why can't we just calculate the exact gradient?
Right, it's too expensive, right? So we're
But it's
calculating.
too expensive, right?
Yeah.
The major motivation of using SGD is that we want to avoid computing exact gradient, because exact gradient requires us to go through the whole data set, right? Which is really very large.
Mm.
If we can afford to check the gradient, say if the norm of gradients are close to zero, then why should we use SGD, right? SGD is approximation of the true gradient.
Could we use the cost function itself then? Would that be easier or still quite difficult? I guess it takes over the entire data set. So
yeah. If you calculate exact loss function, you're gonna go through loss over all the training examples.
Mm-hmm.
Yeah, that doesn't matter for like just 1,000 examples. That's fine. Right? But what if you have like 1 billion training examples? That would be very, very costly.
Mm-hmm.
So that means in practice, right, if you train a neural network on a real world large scale data sets, it's never realistic to diagnose the true convergence. And then how do we determine we should stop? Right? So actually, we usually utilize many other criteria, but I want to emphasize that not any there's not, for those practical criteria. There's no one can guarantee. Okay, you do converge to some local minimum. It's just some like practical heuristics. So firstly, we should realize that, okay, in practice, many large networks are trained on large amounts of data. The model is large, the data is large. So if you use accurate criterion to diagnose the convergence, that is not realistic. And also, we find that you have to go through a data set many times. Many epochs are needed for adequate training. Right? So even you use GPU or multi-core CPUs, if you want to train your neural network with thousands or tens of thousands of epochs, it may cost many hours, even days or weeks. And sometimes to further accelerate, you don't want to put part of the data in the hardware, put part of it in memory. Right? You have to specifically design your hardware. Like Google has developed their own hardware. It's called a TPU. It's not CPU, it's not GPU, it's called TPU. And specifically designed for their own architectures TensorFlow. And if you're interested, you can try to apply for that. If you register their account, you should have like a $300 budget to use that. And I'll try to that before. I have published some paper which based on their TPUs, because our data is kind of too large. I cannot conduct them on some GPUs, standard GPUs. So I use TPUs. It's indeed much faster. So, and then in practice, how can we determine when to terminate the training, right? So the most naive approach will be to set up the maximum number of epochs. Right? I just said, okay, I'm gonna run 1,000 epochs, and then I stop it. That's doable, right? But here you need to be experienced, right, about the setting of number of epochs, and if the number of epochs is too small, you're not sufficient to train. Your model is not sufficient to train. If there are too many, you're gonna overfit the training data, and performance is not good. So in practice, you have to carefully tune the number of epochs you're choosing, right? And threshold on training set error, right? This is actually not very realistic. So usually people is gonna look at a subset of training set and look at the training set error. If that on that subset, the training set error is reduced to some certain level, we're gonna stop. Right? And increased error on validation set, right? The same idea, but they're gonna extract the separate data set, which is called validation set, and they use training set, validation data set, non-overlapping, and then only train on the training set. And then from after every epoch or every 5 epochs, 10 epochs, they look at what is the testing or prediction error on the validation set. If your validation set, the error does not decrease, and then just stop it. So this idea is also called early stopping. It's very famous trick. So as we mentioned before, right? So because the loss function of the neural networks is really highly non-convex, so different initializations can give can go to different local minimums, and that with different performance. So how to avoid bad local minimum, right? So oftentimes people will run several trials, right? Each trial with different random initializations, and then look at the final performance, which one get better performance on the validation set, or you just use majority of voting techniques we have used in boosting or ensemble learning. And as I mentioned before, right, running too many epochs may overtrain a network and result in overfitting. How to avoid that? Use validation data set, right? So the validation data set, you just separate them out, right? And then test accuracy after each epoch, and then say, if you continue to train, then the error on the validation data set start to increase, then you should stop. And someone may and during the setting of the using of the holdout validation data set, right, you can keep tracking the history of the weeks. Like, say I set the maximum number of epochs to be 200 or 500, right? I can just record all the weeks after finishing each epoch, right? And then I just compare after each epoch the performance on the validation data set and choose the set of weights which performs best on the validation data set. And someone may ask, okay, if we do this way, right? So we always need to randomly separate a holdout validation set, right? We're gonna lose some training information. How can we avoid losing the training data, right? We can use cross validation. Right? So remember the cross validation, right? You're gonna separate data set into several parts, right? Like 5 parts meaning that you're doing 5-fold cross validation. Every time I use 1 fold for the test, the remaining folds for the training, right? And I go through like k times and we get k accuracies and average them as the measurement of this particular settings performance, right? And then once we use cross validation to choose the best number of epochs and also other settings, we use that setting to retrain the model on the whole training set, so that we can fully utilize all the training information. Okay? Any questions so far? Okay, so here we want to introduce another very commonly used trick to avoid overfitting. It actually was developed recently. That was not proposed like decades ago. Right? It was developed by Hinton and his students in 2012. Right? So there's one. It's not a joke. It's actually the reality that dropout is a very simple trick, but Google wants to apply a patent for that, file a patent for the dropout trick. They want to forbid other companies and entities to use dropout trick your neural network training. So so it incurs a lot of like criticism. So what is dropout? So you can roughly view as kind of idea of ensemble learning. So the training is like that. At each step, right? Remember when we do the training, right? Every time before we calculate loss, we need to do the forward pass, right? From the input to the output. Right? And before we proceed to each layer, we're gonna use some probability to randomly deactivate or inhibit a portion of the nodes in that layer. So we only use the remaining nodes to compute and then propagate forward. And then we will proceed to the next layer. We first randomly inhibit a small portion of the nodes and use the remaining nodes to compute their values and feed them to the next layer until we calculate the output and calculate loss. And then we do the back propagation. You know, the back propagation, it only back propagates to those activated nodes, right? For those deactivated nodes, we're not going to compute their gradients. So in this way, we can imagine that after every stochastic gradient descent upstate, right, only a portion of the nodes and edges, their derivatives are computed so that their weights are updated, right? So only portion of the parameters of the neural network are updated, right? And this time it might be this portion, and next update might be that portion. And finally, we'll make prediction. You can use all the nodes, all the weights together to make prediction. That's called dropout. And people find that this trick, although very simple, has a fabulous effect, amazing effect to avoid overfitting. This is kind of like a standard procedure implemented in almost all the deep learning libraries. So people found that the dropout trick has some model averaging effect. So you can view like it's kind of like ensemble learning. Every time we update this portion of the weights, you're actually updating a submodel, right? Next time you update that portion of the nodes, you update another model, right? Finally, we'll make prediction because you activate all the nodes. Right? All the nodes and their weights are used to make prediction. You can view it as a kind of ensemble, right? Ensemble all the submodels together to make final prediction. So roughly, the idea is similar to the ensemble learning strategy we discussed before. Okay, so the final discussion is about how do we identify the architectures. Right? So this is mainly determined by the number of hidden units in each layer. Right? So if you use too few hidden units, you're gonna limit the expressiveness of your neural network. So you're gonna prevent the system from adequately fitting the data and learning the concept. You're gonna underfit the data, right? But if you use too many hidden units, meaning that your layers are too wide, then it's easy to overfit the trained data. Right? So how do we identify the optimal architectures of the neural network? Right? So this is a very, very important problem in neural network. And a traditional and effective approach is to use cross-validation. So you can pre-specify a set of architecture candidates, right? Number of nodes and number of layers. And if you want, you can also add a combination of the activation functions, right? Then you can just use cross-validation to evaluate the performance of each particular architecture and pick the one who has the best cross-validation accuracy. Actually, nowadays, people are trying to build up much more powerful algorithms to automatically search for the good architectures of the neural networks for different tasks. So this specific area is very hot. Right? It's called auto ML, auto machine learning. Right? So, like in Google, they have their auto ML. Facebook has, and Microsoft on their Azure platform, they have their own auto ML library. So it's very important. So finally, to summarize what we have discussed so far about neural networks, we introduced the definition neural networks. We mainly focus on the multi-layer perception or feed-forward neural network, and we connect we connect nodes, we organize nodes by layers and connect layers one by one, right? So those inner layers actually learn some representation or transformation of the data, right? So we know that neural networks are highly expressive and it can almost approximate any function, right? Yeah, any arbitrary accuracy. Right? But expressiveness is not always a good thing, right? It has the risk to overfit the trained data, right? So we discussed the harm of the overfitting, right? If your data is noisy, overfitting can lead to bad performance, right? And the key idea for neural networks is how to effectively train. Right? The strategy is called backpropagation. Right? Everybody should understand that principal should be able to implement your own backpropagation algorithm. And because of the time limit, right, we are not able to give a comprehensive introduction of the deep learning and cutting edge research. What is a train, right? But here I just want to briefly mention that it's a vast area. It's a fast-moving area. Right? The researchers in both academia and industry, they're working every day to come out new architectures, new learning algorithms, new accelerators, and new applications. So, and also the modern stochastic gradient descent algorithm for training neural networks are no longer simply naively applying the gradient stochastic gradient descent. Instead, they use some like momentum-based approach, like eta delta, a dam, right? Especially a dam is very, it's kind of like a factual standard in training neural networks. Right? In addition to the feed-forward networks, there are many other networks like restricted Boltzmann machines, autoencoders, convolutional neural networks, and recurrent neural networks. Recurrent neural networks are used to model sequence of data. Like if you have temporal data, how do we do that? Right? And by the way, when you see the progress of the voice recognition, like when you use Alexa in Amazon or some vocal assistant developed by Microsoft and Apple, they're almost all based on the recurrent neural networks, and most common use include LSTM, long short-term memory, gated recurrent neural networks, and if you look at machine translation, they're all about recurrent neural networks. Okay, so now we have finished the neural networks, and in the next again on Thursday, we're going to give a tutorial on Pytorch, the most popular and commonly used deep learning library. I want to advocate that tutorial again, and hopefully everybody will find some time to join. And then our remaining schedule will be introduce some basic learning, logistic regression, and then we'll have our final review. Okay, thanks.